anyway,
Well, let me grab it. And
primarily, I think it's me. I just somehow I'm not clicking.
well, I
Like,
can also let me check before you start feeling that way.
oh,
Let me check something.
well, I saw my anyway.
And it came up before most of you got here this morning, but do keep in mind that it does say at the bottom of your tests that the scores aren't done yet, because I have to go in and hand grade. Not only hand grade a couple of the questions, but also I go through all the questions and look at what's wrong. And oftentimes it's just like, okay, that's a rounding issue, so here's some points back. And so scores do jump quite a bit. Your scores are not done until I go through and edit them. Fair?
Yeah, that sounds good. Any help I can get on that? It just took me too long, and I didn't complete the whole thing. But anyway, that's on me.
So let's see. Yes, 8. So 8 is that empirical rule.
Yeah.
Come on, where are you?
Okay. Well, that's the one.
Why is this being weird this morning? Some days my machine here wants to be weird.
Yeah.
Why is my machine being weird? Oh, is that why? Nope, that is not why. Okay, so that should load up my screen, but that takes a couple minutes to load. So
that if that's the one that you're referring to, that's not the one that I'm referring to.
Oh, okay. Which one were you referring to?
Number 8 on the test.
That's
that
what
one
I've
is
got for
number
number
7.
8.
Well, the one that it talks about the mass about the cornfield.
Oh, the essay one.
No.
No. Well, let me go to
It
yours.
says, you work for a large farm with many fields of corn. And
So there, oh yeah, there were different versions of that one. Okay, let me go in and just grab yours, and then I can see exactly what you were looking at.
yeah, you won't see much.
Well, I can see exactly what you were looking at. That was your 7. No, you want 8.
I was being sarcastic to myself.
Gosh. I know what you were doing.
Okay.
So that was the one with all the interquartile ranges and all those things.
Yes.
With all the data. Okay.
All the data. And I think I might have made a mistake. Anyway, I made a lot of mistakes.
You know, Matt, I was thinking that I think one of the tricky things between doing the interquartile stuff and the standard deviation is, if I'm correct, in standard deviation, you're judging the middle is the mean.
Right.
But in the interquartile thing, the middle is the median.
Yep.
And I think that's confusing sometimes.
And that's one of the things that we've talked about in terms of those 2 sets based on value versus position.
Yeah.
Where value, we talk about mean and standard deviation, and position, we talk about median, IQR,
yeah,
and all the other quartile stuff.
Yeah, that's making a lot more sense to me now.
And you really have to keep those separate.
Yeah.
They don't want to interact with each other.
So I tried to put that into Excel. And show me how you do that again, because where that's in rows instead of columns. So I tried to do that.
So I'm just gonna highlight it,
Okay,
copy. And you could just type it in too, doesn't take that
yeah,
long, but that's kind of irritating, right?
right.
And I'm gonna zoom in on that so it's a little easier to see. And you could get rid of the formatting too. But I'm just gonna grab, like highlight about half that list
Uh-huh,
and move it, just click, hold, move
okay,
to underneath there.
okay.
And I grab that one, but there, you can just put them anywhere you want. But
Yeah,
I'm just gonna brute force move these to a column.
Okay. I
There
gotta
is
practice that.
some command in there, but there's a lot of stuff in Excel I do just by, again, brute force, moving
Yeah.
it around.
Okay,
And then we can sort it nicely, and
all right.
it's in a nice sort list. Again, you could just type them in. You could type them
Yeah.
in the
A.
calculator.
Yeah.
It's all good. So to find the IQR, we would need our medians. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 plus 1 divided by 2 is 7. So we're going to have that middle point at 7. So 1, 2, 3, 4, 5, 6, 7. So that's our median. And I'm just going to make it yellow because that's convenient. And we could use the median tool to have it tell us that that's the median, but we could also just count them. Our upper set is 1, 2, 3, 4, 5, 6. Since it's even, it's going to be in the middle 2 or between those middle 2. So our first quartile is going to be the mean of those 2. Our third quartile is going to be the mean of those 2. So we could just type them in and say, okay, give me the average of those, but we could also just say equal average
Okay.
of those 2. Or you could say equals the quantity, I'm gonna put in a parenthesis, of that plus that in parenthesis divided by 2. It's the same as average for 2 numbers. But then how do we find the interquartile range? We have to subtract those, right?
Mhm.
So our IQR.
Okay.
Again, anytime we want Excel to do something, we have to get equals. And I'm just going to say that value minus, I'm just clicking on them, that value will give their subtraction.
So IQR is 1.
Is Q3 minus Q1, the difference between those 2. So we just said find, I just highlighted the cells. So C13 minus C6, just subtract those 2 cells. And that gave me IQR.
Yeah.
For standard deviation, that's a lot of for interquartile range and the medians, particularly for a small list, just finding those values, counting where those middles are, I think tends to be a lot easier. As you recall, standard deviation by hand, even using Excel to do each of those little calculations is really time consuming.
Mm-hmm.
So for standard deviation, even for a really small list, I'm not going to do any of that. Just equals ST dev, and it's a sample, so ST dev S. Highlight that list. I should be a good boy and end my parenthesis. Enter standard deviation.
Okay.
And if
Yeah.
you type all that data into the calculator instead and go to one variable statistics, it'll give you that same value for your standard deviation. or for your mean, or for any of those.
Yeah. I had a little, yes, I wasn't quite as as careful with the value and the position. I think that's, I just, yeah, that threw
And
it
that takes a
away.
little bit of practice.
Yeah, that's not my middle name lately, but it will be. Well, thank you for going over that. I see where I made the mistakes, and I'll redo it later.
Is there anything else you guys would really like to look at before we talk about probability sum today? Like anybody was like, I really want to see.
The question that had individual, variable, and sample, were you just looking for definitions on that, or examples?
Descriptions, essentially.
Okay.
So, for example, again, the metaphors it had were for someone, were a little different. Suppose you want to estimate yours was percentage of stat students who passed the department final exam. So the individual would be, let's see, the percentage of stat students who passed the department final exam. So the individual scores on those finals, or the students who took those finals, is your different individuals on those individual, you could say individual grades on the final, individual final pass or fail position. You could even just say the students and individual student.
Okay.
You say the estimate the percentage of stat students, it's a percentage, so you're not actually recording what their scores were. The variable is just pass fail. Fair?
Gotcha.
It's essentially categorical data. Fair? And the easy answer there is, or the easy to get wrong answer there is that the variable is the scores themselves. You know, you're not collecting, did they get a 78? You're collecting yes, no, pass, no pass. Sample is those 50 scores. Population would be all students who took the exam. Yeah. So other than that one, that's the idea. And there were slightly different versions of that question, but they were all kind of the same idea. But yeah, just describe those. And as I said, like those all say no to, like, for all of them. I'll put points back in those as soon as I get a chance to look those over. When you do answer stuff like that, always make sure it's a sentence. It doesn't have to be a really, complicated sentence or a long sentence, but it's got to have, subject, verb, even something like it is this, and yours look fine for sentences, but it's not unusual for those to say things like grades. Grades is not an answer. Grades is, answer word problems in sentences. Anything else you guys want to look at? No? Okay. But yeah, I'll get those scores up. It should be today. If your score doesn't move at all, don't panic. That just means either it didn't record what I told it to, it didn't show it, it's not showing it on your side, or I somehow missed yours. Just send me a note and say, hey, but don't panic. Never panic. Also, keep in mind, it takes a little while for us to get kind of in the swing of all these tools. So if it happens that your scores aren't quite what you would like them to be, we do have a lot of points coming down the pipe. Nobody's in a lot of trouble based on test one. Doesn't happen, and no one's sunk because of that. So don't let that throw you off too much. We just got to figure out, okay, what about the interface, or what about how we're studying, or do we have to work on? So don't let a tough test one make you do those. Okay, so let's say Oh, let's do that. So there's a lot of different ways we can talk about probability, but let's use dice, because dice are fun. So we have a die here, and this die has, you know, pips on it. And not only does this die have pips on it, but these pips, that's what the dots are called on a die, if you didn't know that. These pips not only have different numbers, but these pips change color. So that, you know, the die is electronic, say. So when we roll it, it can change color from red or purple or green or orange. That's enough colors probably, right? So the die can come up with those, one of those four colors, randomly chosen when the die comes to a stop. And of course, it's got the numbers, the values, 1, 2, 3, 4, 5, or 6 for the values, the sum of the pips. So does that seem reasonable? So a particular event, and event is a particular result of a random variable. So if we roll the die, we might get, you know, purple 4 as a result. We could get a red 4 as a result. We could get a green 3. We could get a orange 3. We could get a red 5. We could get some combination of a value and a color will occur whenever we roll this die. Fair? Okay. So we want to talk about probability of different events, probability of different things happening. And we'll use some pretty standard notation for this. So that notation will be a capital P for probability. We will use lowercase p for proportion a lot. So do make sure you're making that distinction between the capital P for probability and the lowercase p for proportion. So the probability of some particular event, and we will describe that event, and the probability of that event will be some value. So for example, if we want to say, what is the probability of the color being purple? Well, if we want to find the probability of the color being purple, we have to know two things. We have to know how many outcomes are purple. Well, purple is a single outcome of purple. Out of how many possible outcomes. So how many possible color outcomes are there? I know it's got a big claw, no, a big 4 up there. So yeah, there are 4 possible and one way that event can occur. So 1 out of the 4 possibilities. So number of, I'm going to say ways that can happen. Ways to happen. Technically, number of elements in that event. So number of ways that can happen. divided by the number of total, I'm gonna say total things that can happen. Things possible. Able, possible. Yeah. See, that's why I didn't want to say possible. Nice thing about spelling, you can abbreviate. Full number of things possible. So the probability of the color being purple, 1 out of 4, 4.25. We could say 25%, but I do want us to get used to talking about probabilities in terms of proportions. So I do want to get us used to talking about it in terms of the decimal value. Fair? So just from that description, what is the largest probability we could have? So, question. What is the largest possible probability? So as an example of something that should have a high probability, what is the probability that the value will be less than 10?
Six out of six, or 100%.
6 out of 6. Yeah, 6 of the values are less than 10 out of the 6 possible values. So that's 1 or 100%, right? All of our probabilities, the max they could ever be, the probability of any event has to be less than or possibly equal to 1. That is a rule of probability. No probability can be bigger than 1. Also, what is the smallest number that we can have? What are the smallest numbers of ways something could happen?
0.
Yeah, so let's say, what is the probability of it coming out blue? Well, how many ways does it come out blue? No ways. Out of the 4 color possibilities, right? So not only does it have to be less than 1, it's got to be larger than, or again, possibly equal to 0. So in terms of our rules of probability, that's just other. There are 2 of them. There are 2 unbreakable rules of probability. And rule number 1, the unbreakable rule of number 1 of probability, probabilities are between 0 and 1, including 0 and 1. That might seem like obvious rule, like why do we even call that a rule? But you'd be surprised how important it is. We can never have a probability that's negative, and we can never have a probability that's more than 100%. Can't happen. Michelle?
For the one with the 0, is that supposed to be less than or equal to, or greater than or equal to 0?
Well, the 0 is less than or equal to the probability of an event, so the event is on the greater than side.
Okay, that makes sense.
Okay. It's called a compound inequality, writes it all at once. So 0 is less than the probability is less than 1. So it's an in-between. So we could go through and find, kind of any probability you want this way. So if we wanted to know, say, the probability, oops, I didn't need to write all that. We have that notation. If we wanted to find the probability of being, let's say, of the value being less than or equal to 3. What's the probability of the value being less than or equal to 3? How many ways can that happen? 1, 2, 3 different ways. Out of how many different values can we have?
6.
6. We could reduce that to 1/2, or just say it's a probability of 0.5. Seem reasonable? Okay. What about the probability of, oh, that's kind of fun, of it being a warm color?
Two.
Well, how many of the colors are warm?
2.
Red and orange. We could argue about whether purple can be warm or cool all you want, but let's say for our definition, red and orange are warm and purple and green are cool. Purple's always questionable, but it's more on the cool side. Emil, you said 2. Did you mean 2?
Yeah, I meant red and orange.
2 of how many?
6. 2 of 4. I'm just kidding. Sorry.
2 of 4.
2 of 4 colors.
So be careful. Which one of those is the answer? The 2,
2 of
the
4.
4, or the ratio 2 of 4?
The ratio 2 of 4.
Right. Which we could just express as a proportion if we wanted to.
Right.
Fair? It's really handy when doing this to have the outcomes listed out like this, isn't it?
Yes.
So when we can list out outcomes, that's often quite handy. Ooh. Let me check my chats here. Oh, Kim, you're saying things. Okay. Now let's get a little bit more complicated. What is the probability of getting an orange 5? Uh-oh. Now we've started to mix things, right? If we wanted to, and we could, we're not going to, but if we wanted to, it might be helpful for us to list out all the possible outcomes in terms of both value and color. And we could. Let's even, like, what would that look like? We'd have a red 1, 2, 3, 4, 5, 6. We'd have a purple. I said I wasn't going to do it, but look at me do it here. 1, 2, 3, 4, 5, 6 in purple. We could have a green 1, 2, 3, 4, 5, 6, and we could have a, what's the other one? Orange. An orange 1, 2, 3, 4, 5, 6. So in terms of the color and number combinations, our sample space, our technical term, of all possible different outcomes, that's our sample space. Is that fair? So in some ways, instead of having these problems that we've already done, instead of those being 3 out of 6 or 2 out of 4, we could really look at them out of these 24 possibilities. Because really, that's the different possibilities we're looking at, right? What if we redid the problems based on that? What would happen? Would we get different answers? So value being less than 3, there aren't just these 3 possibilities that are less than 3. There's those 3 possibilities for each color, right? Well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's not 3 out of 6. That's 12 out of 24. It's a totally different, and okay, it's not the same. It's the same answer, just a different way of looking at it. Fair? What about the warm color? Well, we looked at it as those 2 columns out of the 4 columns, essentially. But we also could have looked at it as those 6 and those 6, the 6 red and 6 orange answers. So again, those 12 out of the possible 24. It's the same 0.5. But the orange 5, how many orange 5s are there?
1
There is 1 out of how many?
out of 24.
Out of the possible 24. That seem reasonable? Michelle, you got that brow thing going.
Why is it not out of 1 out of 6? Like if there's 6, 6 different variables that or values you can have.
Well, there are 6 different ways to get a 5, right?
Right.
But it's an orange 5. So there are 4 different ways to get orange.
Okay.
So we got to combine those. Now, we could do it this way always. Go, okay, let's build that combined sample set. But you could imagine this combined sample space getting really big really fast, right? So, Michelle, you actually asked a great question because, like, is there a way to talk about the 6 and the 4 separately? And there absolutely is. This question could be re-expressed as, what is the probability of a value of 5 and orange? Those 2 different things occurring, right? Now, we could break those into 2 pieces. The probability of our value equaling 5 and the probability of orange. What is the probability of the value equaling 5? Now, Michelle, you were saying that was 1 out of 6, right? So, okay, 1 out of 6. What is the probability of being orange?
1 out of 4.
1 out of 4. What operation would this and have to be implying for that 1/6 and 1/4 to combine to make our 1/24?
Just add them.
What's that?
You just add them.
Is 1/6 plus 1/4 1/24?
Yes.
Yeah.
You have to multiply them.
Yeah. I just trying to come denominator.
If we added them, well, let's try adding, see what happens. You'd have to get common denominators, so that you have to multiply by 2 and 2, you get 12, right? And if you were going to add that, you'd have to multiply that by 3 and 3, right? To get 3/12. And 2/12 plus 3/12 is 5/12. Is that 1/24?
No.
No.
Okay.
Andrew, what did you say?
To multiply them.
Multiply them. And the idea that the word and makes us think about adding, you're quite right, Michelle. You hear the word and you want to add stuff. Not in probabilities. That word and in probabilities tells us multiply.
Stupid.
And there's a nice way, I think, to conceptualize that. If we take a fraction, a number less than 1, or a decimal less than 1, and multiply them together, we will always get a value that is smaller, right? And when we put that and in there, that restriction in there, the and makes the chances of something happen smaller. Just having to be a 5 was pretty easy. 1 out of 6, it's about 16%. Being an orange is really easy. That's 25%. But having to be a 5 and orange, that and adds a restriction, right? Makes our probability less. With our numbers less than 1, multiplying is going to make us less. Fair? So and adds restriction on top of restriction. You have to be the right number, you have to be the right color, you have to have the right shoes, you have to have the right type of, it's every and is a restriction. Fair? So that and multiplies. So instead of having to write that sample space out, not that this sample space was all that big, we can combine the two smaller sample spaces by knowing what that and is doing to us. Fair? So let's, kind of take that and say, what if we wanted the probability of being an even number and, well, since I'm writing in purple, let's go with purple. We could count up how many are in the sample space, but also that's probability of being even and the probability of being purple.
1/3.
What's the probability of being even?
Is 1/3. 1/3.
Oh, how many are there?
3, 6.
2 is even, right? 4 is even, and 6 is even. So 3 out of the 6 values. And, says multiply. Probability of being purple, 1 out of the 4. I would certainly encourage you to reduce your fractions before doing anything with them. But then when we multiply those, we would get 1 out of 8. Or 0.125. Now, if instead we had used the fully written out sample space, even and purple would have been that 2, that 4, and that 6, right? Would have been those 3 out of the full 24. And again, is this answer different than that answer? Not when we reduce them, it's not. Cool. So that and, think of and means we multiply, and means our restrictions get lower and lower and lower. Cool. I kind of want to ask a weird question, but what, I'm just going to ask, what is the, what word do you think of as the opposite of and? I know it's a weird question. What do you mean the opposite of and? How about or? And or? So let's say instead of having to be, say, a 5 and green, let's say we wanted to know what is the probability, why am I doing that again? What is the probability of your value being less than 5 or red. Could we do that? So what we need to know, probability of being, our value being less than 5. 1, 2, 3. We're gonna less than 5 means 1 through 4, right? So 1 through 4. And that's 1, 2, 3, 4. But it doesn't, less than 5, it doesn't have to be less than 5 and red, right? So it could be less than 5 and green and still be okay. So that's those 4, those 4, those 4, those 4. There are 16 of those, right? That are less than 4. But wait, or red is these other 2, right? So that's not 16, that's 18 of them. These 12, or anything in the red, cool? Michelle, does that make sense? Are you happy with that? Thinking about it?
Are you asking me?
Yeah. He's like,
Holy
Camilla?
it later.
You can look at it later.
I'll forget later. I'll be like, wait, what? I could just see that one happening to me right now.
Oh, and ors get weird. Out of the 24, so 18 of them qualify out of the 24. And again, we'd reduce that to what, 3/4? 4.75. Now, is there a way we could have separated this? Is there a way we could take the probability of our value being less than 5 or the probability of being red and combine those? There is, but we have to be very careful. This is going to get a little bit weird, so bear with me, okay? So let's say we just tried to handle those separately without worries. Let's say we said, okay, probability of being red. We know probability of being red is 1 out of 4, right? Probability of our value being less than 5, well, 4 of our values out of the 6 are less than 5. Fair? And we have to use some operation to bring those together. Well, what do we want to have happen? If we, every time we have an or, we're adding in ways that we can make it work, right? If you can be, like say, a 3, or you can be green, or you can be orange, every or adds another way to make it work, right? So every or should make our probabilities higher. What operation do we associate with adding in new possibilities? A little heavy-handed to say adding in new possibilities. We should think about adding. And we want to do that. We want to associate that word or with addition. Again, if you're to be allowed in, you have to be a 3, or you can be green, or you can, have a pass, or you can pay the bouncer $10, or every or gives you another way to make something work. It makes the probability go up and up and up. But what happens if we add those? That would be, well, I'm going to turn that into 2/3 plus 1/4. 2/3 is, we have to put it into 12ths, so multiply by 4 and 4, multiply by 3 and 3. I'm assuming all your fractions are really awesome and perfect, right? That would be 11/12, and 11/12 and 3/4 are not the same, right? So yes, we're going to add them, but that didn't quite work. I said we have to be careful, right? Any thoughts on what might have happened to not only make that 11/12 wrong, but notice not only is it wrong, it's also too big. So what could have happened to make that number off and higher than it was supposed to be?
Added instead of multiplied?
Multiply would have made it way smaller, and it should have gotten bigger. So adding was correct, but there is an issue we always have to be careful of when we're using ORs especially. Notice my boxes over here. The less than 5 brought in those possibilities, right? So we counted up all those possibilities. But the red had these possibilities, right?
So that's the addition.
What are we in danger of doing with those two boxes?
Overlapping and not fully counting?
Yeah, overlapping and technically overlapping and over counting,
Or yeah, over counting.
because we're counting those twice.
Yeah.
Fair?
Right.
So technically, whenever we do an OR, to be truly careful with it, if they don't overlap, it doesn't matter at all. If there's no overlap, then you just add them, period. If they do overlap, an OR turns into okay, add them, but you then have to also subtract the group that is both less than 5 and red, the intersection, because you double counted it. So you got to reduce that probability of being red and less than 5. How many of those were there? 4 out of the 24, right? Were both red and 5. Those were the 4 that we overcounted. So if we take this, I'm just going to start over. If we take that 2/3 plus the 1/4 and subtract the 4/24, well, we could reduce the 4/24, right? To 1/6. And again, that was the probability of being less than 5 plus the probability of being red minus the probability of the technical term, the intersection. If there's an intersection, we have to remove that because we've counted it twice. So we have to remove it once. So that's the 2/3, put all those in 12ths. I'll tend to do fraction work pretty fast. If your fraction work is ugly, some of that fast might bother you a bit, stop me, ask me. I'll go through it anytime you want, but I'm going to naturally just try to do them pretty fast. Everybody say hi to Alex. Hi. Want me around the background. So probability of being less than 5, I'm going to put those into 12ths by multiplying by 4 and 4, 3 and 3, 2 and 2. So it'll be 8/12 plus 3/12 minus 2/12. So that's 11 minus 2 is 9/12. And of course, 9/12 reduces to 3/4. That's our 3/4. So ORs can be dangerous because of overlap. So we do have to be careful. Now, we're doing fairly introductory probability. So this kind of overlap isn't going to happen too terribly often for us, and that's good. But it is something that we want to be careful of. Cool. So let's say, how do I want to do that? So many different little kinds of questions we can ask with probability. So let's actually kind of update these rules of probability. So we want to associate the word and gets associated with multiplication. And 3, 4, we associate with addition. I am going to make a little note there where overlap. Again, it's not going to happen too much in the probability that we're going to get in here for us, but it is a big issue when you're doing ORs in general. But even that, the OR is still addition and subtraction. Adding and subtracting go together. And the and language is multiplying always. Fair? And the reason I make a kind of a big deal about that and goes with multiply or goes with add is because it can be, Michelle, like you were kind of, I'm hinting at, a little counterintuitive. When we hear and, we often want to add things together. So you really have to be careful with that. And think about it in terms of restriction. This restriction and that restriction and that restriction makes it more restrictive. We multiply to get those numbers down. Or if it can be this or that or this or that or this, all those ors are adding up possibilities. Every time we put it in an or, we're adding another way things could work. We're adding in value. Cool. So let's say we took the probability of getting a 1 plus the probability of getting a 2 plus the probability of getting a 3 plus the probability of getting a 4 plus the probability of getting a 5 plus the probability of getting a 6. What should that sum equal?
One,
Well, why would you say 1?
because it'll be 6 out of 6.
Well, that would be 1 out of 6 plus 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 1 out of 6. 1, 2, 3, 4, 5, 6. Which you're absolutely right. It'd be 6 out of 6. So if we did the math, it'd be 6 out of 6, which would be that 1. But also notice, in terms of value, we've listed off all the possible things that could happen, right? So what's the probability of getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6? That's almost like, what's the probability of something happening? Well, there's a 100% chance of getting one of those numbers, right? And again, that might seem a little trite, but that is our 4th rule of probability. All outcomes, well, the probability of all outcomes, add to 1. If we knew every possible thing that could happen, we knew the probability of every possible thing that could happen, and we add them all together, being careful about overlaps, they must all add up to 1. because those are all the things that could happen. What's the probability that one of all the things that can happen happen? 100%. Now, this could be surprisingly handy. So for example, if we asked what is the probability of, and my section of rules, what is the probability of not being a orange or red 3? I don't know why I wrote it out. Probability of, oh, that's why, because I used the word not. Probability of not being orange or red 3. That tilde, in case you're curious, it's called a tilde. It's on your keyboard in the upper left-hand corner, is the logic symbol for not. You don't have to know that. I just like to throw in logic symbols because I think it's fun for you guys to know. But probability of not being an orange or red 3. Being an orange or red 3. Now, how many things are not orange or red 3s? There's a lot of things that aren't orange or red 3s, right? And we could count all of those up. But that's irritating. That's a lot of work. What if instead we found the probability of being orange, an orange 3 or a red 3?
So you're saying change the question instead of try and fight for an answer.
Right. I'll show you why. What is the probability of being an orange 3 or a red 3? Well, how many orange 3s are there? 1 out of the 24, right?
Yeah.
Or how many red 3s? 1 out
One.
of the 24, right? So the probability of being an orange 3 or a red 3 is 2 out of 24, which is 1/12. Now, 1/12 is not the answer to our question, right? Our question is, what's the probability of not being an orange or red 3? We know the probability of it being an orange or red 3, right? How is that helpful?
Subtract
What?
from one.
Yeah, what should the probability of not, I'm going to do it this way for the fun of it, an orange 3 or a red 3 plus the probability of being an orange 3 or a red 3? What should that sum be? Well, those two things combine to make everything, right? Everything that's not a red or orange 3 plus everything that is an orange and red 3 should add up to 1, right? So what we found here, this 1/12, is called, technical term, the complement of what we want. It's the other part of what we want. So what are we going to do with that 1/12 to figure out what the answer to our actual question is? 100% minus that 1/12. Fair? That subtraction is going to give us 11/12. That's the probability of not being orange or red 3, an orange or a red 3. So often it is exactly that idea of, well, I don't like this question, I'm going to change it to a question I like better that I can then use to find the answer I want. You will find that math people, particularly good math people, are quite lazy. There's a strong tendency to try to exchange effort for clever. Like, that's a lot of work, finding all the different ways that could happen. You know, it would be clever. Let's find the complement and subtract it from 1. We know that has to work. A lot less work, a lot less effort, but you got to be clever. Fair? My daughter was always asking, would you say that we can be lazy? Only if you're clever. You figure out a clever way to get it done. You can be as lazy as you want, but you got to get it done. You know, lazy isn't easy. You just got to be clever. Fair? So always look for that. Is there a way I could modify this question to make it easier? If you don't want to write out all the sample space, is there a way we could break it up to something handy? If there are way too many possibilities, is there a way we could reverse these possibilities and then subtract from 1, make it easier on ourselves? So we always kind of want to look for that. Is there a way I can change this question to something easier to handle that will still get me what I want? Questions about that? Now, one of the reasons I specifically wanted to do this, color changing die, is because I wanted to have both two different things happening, so we could talk about both and or, and have that intersection happen. Again, that's not going to happen too much in the stuff we're going to do at this level, but it is always something to be concerned about, that intersection where both things are happening, and we have to be careful. As I said, most of the things that we're going to do are going to be a little bit nicer than that, essentially not have these multiple variable outcomes. So one of the classic problems that you kind of want to be prepared for are things like the bowl of marbles. I don't know why math people think there are bowls and bags of marbles everywhere, but they seem to think so. So you got a bowl that's full of marbles. I don't know why I feel the need to draw all these marbles, or such a big bowl anyway. I am not going to draw all these marbles. But you got a bowl filled with marbles. And how many marbles are in this bowl? Say there are, 12 blue marbles. Say there are 10, I've been calling this red, that's been bothering me. It's more like a pink, isn't it? 10 pink or fuchsia. I don't think it matters. So 10 pink marbles. There are 8 green marbles. And, I don't know, how about 6 orange marbles? In this bowl of marbles. So we have some, some questions we can look at here. 1, 2, 3, 4. So what is the probability of getting a blue marble? What is the probability of getting an orange or pink? Now, I should have said that time. Orange or pink. Why don't I just say warm colored marble? Now that we all know what warm means in terms of color. What is the probability of getting a blue and green marble? What is the probability of getting, how about not pink? So take a moment and go through and decide how you would go about those and try to decide what those values are, what those proportions are. While you do that, I'm going to draw more marbles. Presumably because I have an emotional problem. I need to draw more. Gotta do what makes you happy, right? The world's full of all kinds of things. Your life is better off for drawing some marbles. Draw some marbles.
Is pink warm?
Yes, pink is warm.
Okay.
And I would never put a question like that on a test, by the way, because I'm not going to make you guys like, how much color theory do we have to know for this class?
It's more up my alley anyway, so it'd be.
I always try to be careful. A lot of probability questions are about things like, you know, baseball and poker, and, you know, not everybody knows what an earned run average is. Actually, that's how I learned what an earned run average is. I was teaching statistics, and it came up in a statistics question. Somebody asked, and I was like, I have no idea what that is. Luckily, one of the students gave us a lecture on what earned run average is and how it's computed. You didn't really have to know, except that you had to know low earned run average was good and high earned run average was bad. One of the hard things to do when you're teaching is to give people enough time to work on stuff, because you get impatient, you get kind of just bored. It seems like everything's taking too long. So it's actually really good to give yourself something like this to do, so you don't rush people. It's not necessarily great to be muttering to yourself while doing that, because you distract people, but you know, you do the best you can. If I'm going to have a nice drawing board, I might as well use it. Oh, put two blue marbles together. Shouldn't do that. But yeah, real random, that's going to happen, right? Why don't you guys compare answers with each other and see if you're arguing with each other or backing each other up. By the way, if you're bothered by the lack of sporting events during the COVID crisis, go on YouTube and search for Marble Racing League, and you will find a racing league for marbles. They have different, you know, it's done like Formula One racing. They have commentators, they got stands with marbles in them, all made out of Legos mostly, and it's very professionally, it's hilarious. So Marble Racing League, good stuff, in case you're bored. And like marbles. Okay, what's the probability of blue? What's the first thing we have to know to do any of that?
How many there are in total?
Total. Perfect. So there are what, 20, 36 in total? Because all of our probabilities are really part out of whole. Right? How much of the set out of all of them. Now, this does make a big assumption, that part out of whole, if each part or each outcome is equally likely. Now, if they're not equally likely, we'll have to have some conversation. We'll have that conversation. But one of the easy ways to kind of get a little bit lost in this question is to note that there are 4 colors, right? And the probability of being blue, one could want to say, well, blue is one of the 4 colors. So it would be tempting to say one out of the 4 possibilities. But that's only true. This number of outcomes over total number, 1 color out of the 4 colors, is only true if each color is equally likely. Is each color equally likely? No, because there are more blues than greens and more pinks than oranges. There's not the same number of marbles, right? So we can't just say, oh, it's one of the 4 colors, so it's just as likely. That's like saying, oh, well, you know, if you play the $1 million lottery, there's only 2 possible outcomes. You win or you lose, right? That means you got a 50-50 chance, right? Only if they're equally likely, which they are so not, right? So, but each individual marble is just as likely as every other individual marble, right? So there we can, how many blue marbles are there?
Wow.
12, oops, 12. Out of how many total marbles?
36.
36. So that's going to reduce down nicely to our 1/3. And I'm going to put that in decimals just because it's nice. We can keep going, but let's go to 2 decimal places. Is that fair? And Jesse, I think you kind of combined that. You said 1 color, but you knew your sample space was all 36 of them, right? So you were kind of trying to combine those 2 ideas. So careful. Again, warm color, it is 2 out of the 4 colors, but each color's not equally likely, so we can't do that. Each marble is as likely as any other marble, so we've got to go to that level. How many warm marbles are there?
16
16 out of the total marbles?
and 6.
36. So that's going to be what? 4/9, right? 4/9, yeah, 4/9, which is 0.44. By the way, like on your handwritten work, fractions are great. Decimals are fine too, but don't feel you've got to put them in decimals. Most of the class, most of the online stuff is going to be decimals. A lot of our proportional work later on it is going to be decimals. But you know, I'll give you a thumbs up for fractions because fractions are better anyway, right? I can prove that to you if you want. The fractions are better. You guys like fractions better than you like decimals, I promise.
Okay.
If you doubt that, let me know and I'll prove it to you. Michelle, do you doubt that? You don't doubt that? Good defensive move there. No, I don't. Fractions clearly better. So what about blue and green? This is the trap question, right?
1236 times 836. I didn't reduce my fraction right there. So it's 1/3 times 2/9.
That's the trap. Because how many marbles are both blue and green?
Yeah. Oh.
0.
None.
Oh, that's dumb.
Yeah, I know.
Oh.
Oh, that's tricky.
I only put that in because Svetlana drops that into some of the homework every once in a while. So be careful about that. It's essentially the and version of that intersection. For an and to be valid, for that multiplication to take place, both have to be valid. Notice when we did it up here, that and, I erased it. It was a color and a number, right? They were
Yeah.
different sets. They weren't mutually exclusive. So be careful. If your and is mutually exclusive, 0. That, and I totally think of that as a trick question. And like, if I put that on a test, I would feel horrible about myself in the morning. Doesn't necessarily, I wouldn't do it. I'm okay with feeling horrible about myself, but I wouldn't do it. So careful.
Okay.
Careful. Put a little evil smiley face there. Probability of not pink. We could add up everything that's not pink. We could do that. It would be 12 plus that's too hard.
Why don't we just, ask the other question?
Why don't we just look at 1 minus the probability of pink? That's easier, right? Presumably. So 1 minus the probability of being pink, and pink is 10 out of 36, is the other 26 out of 36, which would reduce to the always beautiful 13/18, which is far from beautiful. It's an ugly number, but that's why fractions are nice. If you like fractions, you're done. If you like decimals, you got work to do. So liking fractions will save you trouble.
Huh, I did that.
So, with the exception of this question being evil, these are much more the types of things I kind of expect us to want to be comfortable with as we go into our discussion on probability. Now, this is essentially chapter 5. If you want or more interested in probability than this is the probability that we need for our discussion in 6, 7, 8. Because we need to be able to chat about probabilities. And the big thing about those chats about probabilities are they have to be less than 1 or bigger than 0. They have to add up to 1. Or means we add, and means we multiply. Those 4 things are what we need. Chapter 5 does give you a more general introduction to probability. It'll talk about that intersection thing. It'll talk about some other neat tools with probability. If you're interested in probability, dive into that section. But you'll notice we don't have a chapter 5 set of homework. We just have that one sheet. Fair? And that sheet is essentially a bowl of marbles problem. I think it's a bag of tulips instead of a bowl of marbles. Same idea. Fair? So mostly I just want to make sure that these 4 rules for probability make sense and seem reasonable. So tomorrow we can jump into our chapter 6, nice and solid and fairly happy. So some of this talk with the dye and the colors, probably a little bit more than we need, just to give us a nice conversation to have. From a work standpoint, as long as these 4 questions seemed reasonable to you, you should be in fine shape for what our discussion is going to be. But if you're more interested in probability than that, then, you know, be very happy to, you know, dive in, read more of on chapter 5. But we're going to take what we want from 5 and jump into 6. Questions about that? Anybody want any hints or tips about drawing marbles?
Ugh.
I have a question.
Is it about Martin? No, okay. Yes, what's that?
Oh, I love marbles. If you have a little time, well, anyway. I am sure that the probability is somehow going to merge into statistics.
Oh, yeah.
Okay. That's just, I guess, just a
Well,
statement.
and it already has. When we talked about things like what proportion of people or what proportion of values will be between the first standard deviation and the, or plus and minus the first standard deviation. Well, 68% is in there, right?
Right.
Switch that question to what is the probability of being in that range? 0.68.
Okay.
Those percentages are probabilities. Fair?
Fair.
What if it's between 1 standard deviation or above the halfway point? Well, that's that upper 50% plus that 68%. Wait, we didn't add the plus 68%. We took the 50% and added the 34%, right? Because of the overlap. Those are already probability questions. They're just hidden as probability questions. And I said later on, particularly in chapter 7, we'd get more complicated about, well, what if it's not 1 standard deviation? What if it's 1.5 or 1 1/3? Well, then the probability discussions get a little bit more complicated. We need a little bit more language. That's why we're doing this.
Okay.
Fair? So yes, it'll absolutely intertwine, and frankly, it already has. Like that question, that's always good to go out. It's always good to be thinking, how is this going to interact with what we've already been talking about? That's a thinking question. Lots of respect for that. Can you want to stay and do homework or log back in? No, you're talking to Kim. Great. Anything I can do for you guys before you wander off today? No, you guys are good? If you guys want to hang around, let me end this meeting and then you guys restart it. Mostly because that will start the conversion of the recording for it, and it'll let me get it up online faster.
Okay.
Fair. But I really like that you guys tend to hang around, tend to use that Zoom and talk to each other.
Yeah.
For those of you who are doing that, that will make a huge, huge difference as we go along. So do keep doing that. If you got other guys are kind of thinking, maybe I should do that too during week 7, because it's always best to do that during the last week as opposed to all. Don't. So if you're thinking maybe you'll do that later, just dive in and start doing it. But it is handy for me to be able to close it down so I can get that online thing faster. Okay.
Okay. Thanks, Matt.
Mhm.
And I'll come back. Yeah.
Log back in, Jesse.
Okay. I'll see you guys tomorrow.